Hey, what's up everyone? Today we're going to be doing the oxidation reduction section of the 2024 USNCO local exam. So this is from questions 37 through 42. Let's start with question 37. What is the oxidation number of carbon in methanol, CH3OH? So we have CH3OH, and certain elements are going to have fixed oxidation numbers. For example, oxygen is almost always -2, and hydrogen is almost always +1. So if we add up the fixed oxidation numbers that we know, we have -2 plus 4 hydrogens times +1 plus X, which is going to be the oxidation number of C, and all this is going to sum up to 0 because this is overall neutral. So this comes out to 2 plus X is equal to 0, so X is equal to -2, which is answer choice A. Let's move on to question 38. A standard galvanic cell is assembled from silver and platinum in 1 molar solutions of the corresponding metal ions. Which metal would be labeled the cathode, and what is the voltage of the standard galvanic cell? So the standard cell potential, E cell, is equal to the cell potential of the cathode minus the cell potential of the anode. And for a galvanic cell, which is what we have here, your E cell overall is going to be positive, greater than 0. So with the numbers that are given, 1.2 and 0.8, the only way we could find the difference between them for the entire thing to be positive is if 1.2 is the cathode, or the platinum is the cathode, and 0.8, or the silver, is the anode. So the overall cell potential is going to be 0.4, and our cathode is going to be the platinum. So that is answer choice D. Let's move on to question 39. A spoon is electroplated in a solution of 1 molar silver nitrate with a current of 0.1 amps. How long does it take to plate 0.1 grams of silver on the spoon? So when it comes to electroplating, what we're really doing is we're taking the silver nitrate, which is AgNO3, and specifically we're taking the silver ion, so Ag+, and we're adding an electron to it to form a silver solid, which is going to be plated onto the spoon. Since the charge on the silver is the silver ion is +1, we only need 1 electron to convert the ion into the solid form. So we know that we are going to need to plate 0.1 grams of silver onto the spoon. So first let's find out how many moles that is. So we have 0.1 grams, and if we divide by the molar mass, which is 107.87 grams per mole, that's going to tell us that we have, so 0.1 divided by 107.87. This tells us that we're going to have 9.27 times 10 to the -4 moles of silver. Since we know that the silver and the number of electrons are in a 1-to-1 ratio, then that means we also need 9.27 times 10 to the -4 moles of electrons to fully plate this amount of silver. Now that we know how many moles of electrons we're going to need, we need some way to relate this to time. So how do we do that? Well, we use the current. We know that we have, it's a 0.1 amp current, which is the same as 0.1 coulombs per second. Coulomb is a dimension of charge. And so now we need some way to relate coulombs to moles of electrons. And we do that using Faraday's constant. So Faraday's constant tells you that for 1 mole of electrons, the charge associated with that is 96,485 coulombs. So if we do out that calculation, divided by 96,485, that tells us that every second we are getting 1.04 times 10 to the -6 coulombs. So that's how many, moles of electrons, per second. That went a little off frame, but hope that's fine. And so now that we have a rate and we know the final amount that we need, all we really have to do is divide these two numbers. So we divide the total amount by the rate, and that tells us that we need to let this run for 894 seconds. And the answer choices are in minutes, so let's divide this by 60. And that tells you that we're gonna need to run this for approximately 15 minutes. And that is answer choice C. Let's move on to question 40. Aqueous sulfuric acid containing 0.1 molar sodium iodide is electrolyzed at glassy carbon electrodes. What is produced at the anode? Now remember, at the anode is where oxidation occurs. Oxidation. And if you have trouble remembering oxidation and reduction and where it happens in the anode or cathode, I don't know, there's something that I came up with a long time ago, an ox and a red cat. If you remember this, an ox, anode, oxidation, and then red cat, reduction, cathode. It helped me, I don't know, I came up with it. Regardless, what happens at the oxidation step is that electrons are being produced. So we have a couple of different options here. We can either oxidize the sulfate ion, we can oxidize the iodide ion, or we could oxidize water. Now, we can almost immediately get rid of water, because water, in order to oxidize it, we have to break 2 of these OH bonds, and that requires a lot of energy. So it's unlikely that this will be the first thing to be oxidized, because it requires so much energy to break these OH bonds. It's also a similar story for the sulfate ion. So if you look at the Lewis diagram for sulfate, it's going to be 2 single bonded oxygens and 2 double bonded oxygens, and the negative charges are on the single bonded oxygens. However, you can draw multiple different structures for the sulfate ion. Instead of having the single bonds adjacent to each other, you could have them opposite from each other. And so you could have a structure that looks like this, and you could have a lot of other combinations. You could have this and that be the single bonds. And there's a lot of different variations. In fact, there's 6 different variations. And these are what we call resonance structures. They're different Lewis structures for the same compound. And what happens in resonance structures is that the overall structure of the compound is a combination of all these resonance structures. So these excess electrons are kind of delocalized throughout all these resonance structures. This makes sulfate quite stable. It's hard to remove these excess electrons. It's hard to oxidize this because of how many resonance structures there are, which contribute to the stability of the compound. So sulfate is also unlikely to be the first thing to be oxidized. It's not likely to be oxidized. So the last thing that we have to look at is iodide. The iodide ion is almost a halogen. It's almost iodine. You've taken iodine and you've added an excess electron to it. And remember, iodine is a pretty big atom. So when you add an excess electron to that, there's not much force connecting this electron to the nucleus of the iodide ion because of how much space there is. There's a lot of shielding, there's a lot of space. So this electron kind of wants to leave. It doesn't take a lot of energy for this electron to leave. And it takes a lot less energy than it would to break up the water or to remove an electron from the resonance stabilized sulfate ion. So the iodide ion is most likely to be oxidized. And so if iodide is being oxidized, remember this means that we are pulling out electrons from the iodide and producing electrons. And of course, you can't just have iodine on its own. It's going to be I2, so that's iodine. And so in order to balance this, you get a 2 here and a 2 here. So what is produced at the anode? Remember, the iodide is being oxidized to produce iodine, which is answer choice C. Let's move on to question 41. A certain galvanic cell has a cell potential that increases with increasing temperature. What best explains this observation? The best way of relating cell potential to temperature is using Gibbs free energy. Remember, you have 2 equations for Gibbs free energy. The one that you learn in thermo, which is that it's the change in the enthalpy minus T delta change in the entropy. And you also have an equation for Gibbs free energy that you learn in electrochemistry, which is that the change in the Gibbs free energy is equal to minus NFE standard, where N is the number of moles of electrons, F is Faraday's constant, and E is your cell potential. So if we set these 2 equations equal to each other, minus T delta S is equal to minus NFE, and we factor out a negative to make this simpler, we get NFE standard is equal to T delta S minus delta H standard. We know that the cell potential is increasing with increasing temperature. So as we increase temperature, E cells should also increase. And if you realize from this equation, the only thing necessary for that is for the change in the entropy to be positive. Because if it were negative, as you increase the temperature, your E cell would go down. And in fact, that's the only thing necessary. It doesn't matter what delta H is because that's just a constant. N and F don't really matter. They're both effectively constants. N is the number of moles of electrons transferred in the galvanic cell, which is effectively a constant, and F is a constant. So the only thing that really matters is your delta S, and delta S has to be positive. So if that's positive, then as you increase temperature, then your E cell will also increase. So the correct answer is answer choice B, that the change in the entropy of the reaction should be greater than 0. Let's move on to question 42. What is the standard reduction potential under acidic conditions for the reduction of PbO2 to PbS? If you look at the overall reaction, you can see that it's the sum of the two half reactions that we're given. And we're also given the cell potentials of these half reactions. And so all we really have to do is sum up the cell potentials. Because if you sum up these half reactions, you get the overall reaction. So if you sum up the cell potentials, you get the cell potential of the overall reaction. So 1.468 plus minus 0.126, that is 1.342 volts, which is answer choice C. Now, there is a bit of complication with this problem because the answer key says that the answer is answer choice A. And the way you get that is by treating the E cell as an extensive property. So what that means is that you have to multiply the E cell by the number of moles of electrons transferred in the half reaction. So for the first one, it's 2 times 1.468 plus also 2 for the second reaction times negative 0.126 divided by the total number of moles of electrons, which is 4. And if you do this, you get 0.671. But this isn't correct because E cell is an intensive property, meaning it doesn't depend on the number of moles of electrons being transferred. So this isn't necessary. And therefore you get your original calculation of 1.342. Now I've reached out to ACS, I'll let you guys know what they say. But I do believe this is a mistake according to what I've seen online and of course my understanding of it. I believe the correct answer is C. If someone knows otherwise, please feel free to correct me and I'll let you guys know what the ACS says. Other than that, that's the entire section. I hope that was helpful. I hope you were able to learn something. Please consider leaving a like and subscribing, and I'll see you guys next time. Thank you.